Welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel where we talk about everything I want to, science and math. And today we are finishing up the notes for Atoms and Energy, Unit 3, in our playlist, Chemical Elements. And we did a problem that I forgot to record, so I'll go over it real quick. And we had a student who wasn't here anyway, so he'll get to listen. Okay, so here's our example problem. Got your notes out? Get your notes out and follow along. So this is the second kind of problem that's going to be on the test. The first kind of problem is balancing nuclear equations, and you're going to have 2 worksheets for homework to do with that tonight. Put away your phone. So copper has 2 naturally occurring elements, isotopes. Copper 63 with the abundance of 69.17, and copper 65 with the abundance of 30.83%. Step 1. You change these percents into decimals by moving the decimal place 2 places over to the left. Everybody remember that from elementary school. Next, what you do, see if I can get this to scroll up. Ooh, it did. Next, what you do is you write down the masses, those are the masses of your 2 isotopes, and you multiply them by the decimal point, and then you add them up, and that gives you the answer. So that's not too bad. The third kind of problem is we have 3 isotopes of oxygen. Oxygen 16, 17, and 18. And the question is which is most abundant? How you get the answer is you look at the mass on the periodic table. Our mass is 15.99. Which one is that closest to? Oxygen 16. So the answer is oxygen 16. And I bet somebody didn't mind hearing that again. All right, so now we're going to learn something brand new you've never learned before, which is very exciting. And it is the quantum physics or quantum chemistry, and it's the modern idea of the atom. And it is that electrons can be described as a particle or a wave, and I have a demonstration to show you tomorrow with that. They also can leap between energy levels, and it's called a quantum jump or a quantum leap. So quantum leap. There used to be an old TV show back in the 90s called Quantum Leap, and I have never seen it. But a girl in the other class says she's seen every show and she's got them on DVD. She loves it. So maybe we should watch Quantum Leap. I think it has nothing to do with this, though. I think it has to do with time traveling, but I've never seen it. Have y'all ever seen it, Quantum Leap, from the 90s? I think he has a mullet, too. Not sure about that. All right. Oh, is that the one? Okay, so what this is talking about is, remember, the modern view of the atom, you have the nucleus. Then the electrons hang out in clouds. They can jump between the levels, these orbitals, and that's a quantum leap. What we're going to do is we are going to learn about how to tell where those electrons are. Now, if they are at the lowest energy level possible, it's said to be at the ground state. That sort of makes sense, doesn't it? The ground state. If they have jumped up to a higher energy level, they are said to be excited. They're at the excited state. They're all excited and happy, and they jump up. I have to write real slow or it stops responding. Excited state. Now, remember our video, Atoms Ring of Truth. They jump up to these excited states, and then they give off their extra energy, and they jump back down. And remember the video, we go whoop, whoop. And what did they give off that extra energy as? Do you remember? I think she mouthed it. What did you say, Rosa? Yes, they give it off as light, electromagnetic energy. It's not just visible light, it's all of it. So they give it off as electromagnetic radiation, will be the word we use here, but it's light when they leap down the energy levels. And it's all of the electromagnetic radiation. Ronald McDonald is very ugly, extra gross. Radio, microwave, infrared, visible UV, X-ray, gamma rays. These are produced in the sun and other stars. They all travel at the speed of light. That's why if have a radio station in Atlanta, it's not coming to you at the speed of sound, which is very slow. It comes to you at the speed of light, and then your radio translates it into sound again. It goes from sound to speed of light to sound again. All right, now, next idea, quantum numbers is like an address. I'll move this way up there. Whoop, not that high. It really doesn't want to go in between. Come on. I have to just leave it like that. Yeah, I'll leave it like that. Okay, so if I send a letter, I could send it to Overcomer. And of everybody in the whole world, it would go to him. And we'll just pretend what your address is. We don't know what it really is. Okay, so first of all, I write on the address that it's going to go to the United States. And that gets rid of all the other countries in the world. It's not going to go to them. It's only going to go to the United States. Then I'm going to have Georgia in the address. And it's not going to go to any other state in the union. And it gets rid of all those other possibilities. And the only addresses being considered are ones in Georgia. And then if he lives in Dallas, where the school is, then I would write the city Dallas, and that would get rid of all the other cities in Georgia as a possibility. Then I would write his street name, and that would get rid of all other possibilities of streets in Dallas. Then I would write his house number, and that would get rid of the possibility of every other house on his street. Then I would write his name on it, and it would go to him and no one else in his family. So out of everybody in the whole world, that address will send that letter to him. Does that make sense? Well, electrons have an address too. They're called quantum numbers, and they only need 4 of them. And it tells which orbital they live in going around the atom. There's different orbitals. Remember, we learned about these different orbitals in our Bohr models. And now we're going to learn how these numbers can tell exactly which electron it is within the atom. Can everybody imagine that big idea? Okay. So these are called quantum numbers. Now, this is what makes this confusing is they call things more than one name. Why don't they just call it one thing? I don't know, but they do. The first quantum number is called the first quantum number. It's also called the principal quantum number, and it also is signified by a lowercase letter n. That makes no sense because a lowercase letter n stands for neutron, but it also stands for the first part of the electron's address, called the principal quantum number. And it's telling which level it lives on. And so I want you to look over here and also at your periodic table. These levels are reflected in the periodic table, and the levels are 1 through 7. Remember, Mendeleev didn't invent the periodic table, he discovered it. The patterns were always there. And there's always been 7 levels that the electrons can live on. Okay? Look at your periodic table, and do you see those numbers 1 through 7? Those are the first quantum number. They tell which level the electron lives on. Number 2, the second quantum number, is also signified by a lowercase cursive L. So that's why you had to learn cursive. Did you ever learn cursive? A lot of kids nowadays don't learn cursive. Did y'all learn it?
No.
See, some of y'all, no. It was a big deal when I was in 3rd grade, but now they've got rid of it. And there are kids who don't know how to read that clock and don't know how to read cursive. And we spent a lot of time on both of those in 3rd grade. All right, so the second one is the L, and it tells the shape of the orbital. The orbitals come in different shapes, and the shapes, some of them are more attractive to an electron to live in than others. Just like you. If you were getting an apartment, you would rather have the nice apartment that's got lots of bedrooms, and it's got a walk-in shower, and it's got a hot tub on the deck, and it's got What's something else? A walk-in closet. You want the good apartment, right? Well, the electrons are the same way, and they like them in this order. They like S better than P, better than D, better than F. Nobody wants F. So sometimes electrons will hop up an extra level just to get a better looking apartment, right? Now, these shapes, and these are our L's. I didn't do cursive, I just did a regular L. The first one can be signified by the number 0 or the letter S, and it looks like a sphere, and there's only one type of room. One sphere-shaped room, and they like it best. That's the primo room, the one they all want. The next kind of orbital can be signified by the number 1. It is also signified by the letter P, and it is said to be dumbbell-shaped, but I don't think it looks like a dumbbell. I think it looks like the number 8. And it can be oriented on the Y, the X, or the Z axis. And there's 3 different P rooms. And they can be on Y, X, or Z. Okay, we're feeling all right so far, learning this brand new idea. The next kind of room is D. D's look like fat plus signs, and they can be on the X and Y, or they can be between the X and Y, or they can be on the Y and Z, or they can be between the Y and Z, or they look totally different. So I'm going to draw it like a fat plus sign going X and Y, and then going between X and Y, and then since our paper's 2D and not 3D, I'm going to draw it again like that, and then again like this, because that would be on the Z axis, and then the last one looks to me like 2 baby pacifiers stuck together. And those are the 5D rooms that are available for the electron to live in. The last one is pretty easy to remember. Is signified by the number 3. Is signified by the letter F, and they're fuzzy looking. So F for fuzzy, S for sphere, F for fuzzy, and we're not even going to try to show you what they look like. We're just going to draw 7 fuzzy little dots. 7 fuzzies. 7. Okay? Nobody's cried. Nobody has a rash. I think we're doing good so far.
But like a cotton ball.
Kind of like cotton balls, yes. They're the fuzzies. Okay, now. So here is a picture I copied of them. See, S for sphere. P, this P is on the x-axis. You can have it on the y or the z. There's the D, the fat plus, and the F has got all these little things sticking out, and they end up looking fuzzy. Now, the third quantum number is signified by M, lowercase m sub L. And it tells which type it is. Is it P on the X, Y, or Z? Is it D on the axes or between them? And that's the third quantum number, or M sub L. This will make more sense when we play a game with it, so don't panic. The fourth quantum number tells which way the electron spins. If up to 2 electrons can be in the same room, just like you guys, some of you sadly have to share a room with your brother or sister. I had to share a room with my sister, and boy, did we fight. We'd get out the tape and put it down the middle of the room and say, "You can't go on my side." And then my sister had the side near the windows, and she'd say, "But I have to go on your side because I have to be able to leave the room and go in the bathroom." And I'm like, "No, out the window. My side has the door." We just fought and fought. So my parents, being bad parents, rewarded us with Gail getting her own room. We should have gotten punished and been made to stay in that room and fight, but we didn't. We each got our own room. She got a nice room in the basement. She had to go to the basement. All right. I'm sure that y'all never act like that. Y'all are good children. Y'all don't fight with your brothers and sisters.
Yeah, we don't talk.
Or else y'all are all rich kids who have your own room and you don't have to fight with your brother and sister. Maybe that's it.
Not over here.
Wait, what's that next to the M?
It is a lowercase cursive L. So it's M sub L. And then the last one, if they share a room, one will spin clockwise and the other one will spin counterclockwise. That is signified by plus or minus 1/2. And this letter is called M sub S, which kind of makes sense, S for spin. Which way is it spinning? Now then, we're going to learn how to write electron configurations. You're like, oh, great. And there's rules to it. Just like how there were rules when we learned how to do significant digits. And these are the rules. The first rule, these rules were named after the people who invented them. The first one is called Hund's rule. Hunds. Hund's rule, not Hut, like Jabba the Hutt, but Hun. Hund's rule. In orbitals of equal energy, they each get an electron before they double up. And this is just like at your house probably. When my husband and I had kids, we had a 3-bedroom house. And so we got 1 bedroom. And then we had the first kid, he got a room. Then we had the second kid, he got a room. But then came along the third kid, and somebody had to double up. The oldest got his own room, and the 2 little ones had to share. So that's probably at your house too. You probably got your own room until there were too many kids, not enough bedrooms, and then you have to start doubling up, right? So that's the same thing the electrons do. It's called Hund's rule. The next one is called Pauli's exclusion principle. Pauli''S. And this is if they share an orbital, if they're sharing a room, one spins clockwise and the other one counterclockwise. And how we show this, if we are drawing the configuration, is by arrows, and you draw one up and one down. That signifies one is spinning clockwise and one is spinning counterclockwise. One thing that makes this confusing is there are more than one way to show these. One way is by arrows, and then another one, the way I'm going to show you in a second. The third rule is that the lowest energy level fills first, and you can know which fills next by 2 ways, either the periodic table or a chart. So it's not that things just everything on 4 fills before everything on 5. No, it goes by this chart. If you write these letters down in this way and these arrows this way, it shows you what fills in next. I don't like this way. Mr. Myrick uses it. If you like it, go for it. Why I don't like it is if you forget that you go 1, 2, 2P, 3S, if your arrows get off, you're going to miss all your problems. So the way I do it is by the periodic table. But I'll explain them both to you. You do you. You do whatever works for you. All right, so let me show you how to do it. Oh, and there's also another way to do it, a shortcut way called the noble gas configuration. And I'll explain that one to you too. It's written as a shorthand way to write it. All right, so this is our new skill we're learning, something hopefully you've never done before. So you get to learn something brand new today. And we're going to do something called writing electron configurations. I forgot to sing the song last period. I'll sing it for you now. It goes like this. 1s2 and 2s2 and then comes 2p6. Electron configurations, yes, they're really slick. I'll sing it again later if you want me to. All right, so this is how you do it. Step 1, you look on the periodic table and see how many electrons it has. So how many electrons does hydrogen have? 1, right? The number of protons is the number of electrons in the neutral atom, and the number of protons is the atomic number, and this whole number that goes with hydrogen is 1, correct? Okay, so now we are going to write where that electron goes, and we can tell by the periodic table. If we look at the periodic table, we know that hydrogen is right here. Its electron is going to go on the first row. And we also know it's going to be an S-shaped room. Over this block, I want you to write S. Now the other class said it's already on there. Is there an S already written right here over these two columns on your periodic table? If not, I want you to write it on there. These, I want you to write D over. These 10 right here, write D over. These 6, I want you to write P over. And down here, by these, I want you to write F.
Yeah, there's like it.
It's already on there?
Yeah, it's like on the side, like right here.
Okay, well make sure you understand this. This is how you're going to use the periodic table. The other thing is, make sure it's got numbers 1 through 7. Go back up too. I'll have to stick that there later. Make sure it's got a 3 right here. Make sure it's got 4 and 5 right there. Okay? And I'll show it to the video people. Video people are going, this is a very lame video. The video teacher just left. Okay, so what you're going to do is you're going to write 1 through 7 on your periodic table here. These, over these, write S. Over these, write D. Over these, write P. By these, write F. Also write a number 3 right there, and write a 4 and 5 right there. Okay, and we're going to use our periodic table to figure out the electron configuration. All right, so on our periodic table, hydrogen's right here. It's on level 1. So its first electron is going to go in level 1. It's going to go into an S room because we have S over that block, and it has 1 electron. Okay, how do we feel about that? It's got on level 1, it's an S-shaped room, and it's got 1 electron in it. Good?
Is that it?
That's it. So let's do helium. Look on the periodic table. How many electrons does helium have? 2. Now this is a little bit confusing. I'm going to show it here to these people, and then I'll show it to you. You can think of the helium square as being right there, because it is going to have its electron go in the S block. Now I'm going to show you all on the big one, because if that was too little. I want you to imagine that helium is not here. Helium is on that square, that blank place right there. Helium puts its electrons in an S-shaped room. Is everybody okay with that? Donald? Jalen, tap Donald for me. Donald, now keep your head up. You understand this? This is hard. Sierra. Mackenzie, tap Sierra. Sierra, wake up. This is hard. You gotta pay attention. This is brand new. You will have never learned this before. You gotta pay attention to understand it. So pay attention. We want to pass chemistry. Chemistry is a great class. All right. So helium's electrons are on the first level. They're in an S-shaped room, and there's 2 of them. How do we feel about that? Okay, let's try lithium. Lithium is number 3. Lithium's first 2 electrons go into a 1s room. Its next electron goes into a 2s room. I'm going to show you on the periodic table. Here's lithium number 3. The first 2 electrons go 1s, and there's 2 of them. The third one is in a 2s room. Can you see it, Donald? You see it? Sierra, let me see your eyeballs. Don't put your head down. You're not going to understand this if you don't pay close attention. Okay, let's try the next one. Nitrogen. So, where are the first 2 electrons of nitrogen going to go? Into a 1s room, right? And then, nitrogen's number 7. So the first ones go into the 1s room. The next the next 2 go into 2s. And then the next 3 go into 2p. And I'll show you that on the periodic table. So let's look at it. Nitrogen is right here. we're going to use the periodic table and write its electron configuration. The first two go into 1s, 1, 2. The next two go into 2s, 3, 4 go into 2s. Then over here, these are p's, and nitrogen has got 1, 2, 3 of them. So the next 3 electrons go in to 2p. So it's 2p3. Making a little bit of sense? So let's do fluorine. 1s2, 2s2, then 2p, 1, 2, 3, 4, 5. Sure. Want to do another one? Let's do aluminum. We're going to play a game with this. 1s2, 2s2, 2p6, 3s2, 3p1.
That makes sense.
It makes a lot more sense when you did that.
Did that make more sense with aluminum?
Yes.
So this is telling us that chart. The chart is telling us the same thing. But the periodic table you're not going to get off on. Your periodic table will tell you the right answer. So I like it better. Now, let me show you the noble gas configuration. Imagine if you were doing something like 10. It would take a long time to do 10, wouldn't it? So instead you say it's just like krypton, except then it's got 5s2. This actually drops down, so that's 3, that's 4. So it's 4d10, and then it's back to 5p2. Same as krypton, except this little bit. And I'm going to explain that more to you later. So to do the noble gas configuration, you write it like this. So if we were going to do lithium, we could say that lithium is the same as helium. Notice that helium is the noble gas that comes before lithium. It's the last noble gas before lithium. So I say it's the same as helium, except it's got 2s1. Same as helium plus 2s1. Nitrogen is the same as helium. Helium is the one before nitrogen too. Same as helium, except it's got 2s2, 2p3. Now, those of you who have this periodic table, the reason why I said I wouldn't let you use it is if you look on it, it's got the noble gas configurations on it. They're written on this periodic table, if you look at it. So we can't use this one on this test. We're going to have to use the other one. It gives us too much information. We don't want you just to copy them down. You got to know them. All right, we're going to play a game with that tomorrow. If it doesn't make sense, it'll make more sense tomorrow. Okay, so this is our last couple of little ideas. The first one is from our video, Adam's Ring of Truth. When he drove around and looking at the rainbows given off by the neon signs. Remember that with the cool jazz music playing in the background? And then he had the electrons that were hopping up, and then they'd hop down and they'd go whoop, whoop, whoop. And then it would give off light. Do you remember that a little bit? Because every atom is different, and every atom has a different electron configuration. Each one has different orbitals, which make it give off different light patterns. They give off as if you excite electrons with heat or electricity, they will jump up to higher orbitals and then give off the extra energy as light, or really any part of the electromagnetic spectrum. Because each atom has a unique orbital pattern, they give off unique light. Bands of light like a broken rainbow. It is an atomic fingerprint. And he even said those words, if you remember it. Each atom, we can tell what it is by looking at its rainbow it gives off, and we know which one it is because that rainbow, those bands of light called an emission spectrum, correspond to only one atom, and we can identify atoms by their rainbows. We're going to do a lab with this on Thursday. We're going to have rainbow glasses and a little rainbow machine thing, and we're going to look at the bands of light. Now, every year, just about it, I've had kids figure out they're colorblind when we do this lab, because it's such pure color, complete bands of light will be missing, and they'll realize that they're not seeing all the colors. I had one fellow a long time ago. His name was Marcus. Not this Marcus, a different one. And he got so upset when he figured out, because of this lab, that he was colorblind. And I was like, why are you so upset? You're the same person you were before chemistry class as you are now after chemistry class. He was about to cry. And he said, but Miss Blackburn, before today I thought I was perfect. Like, nope, you're not perfect, Marcus. Not you, Marcus, the other Marcus. Long time ago, Marcus. He was so upset. I'm like, you are who you are. You see how you see. You know, don't take it such to heart. Okay, now just a couple of other little tying up loose ends, things that I probably should have already said by now, and we did when we talked about density, but I wanted to make sure you know the difference. The difference in a chemical and physical property. A chemical property tells how something changes as it reacts. How it reacts with something else. The symbol in chemistry for change is the Greek letter delta. It's a triangle. You never have to write change or difference in math and science again. You can just write a triangle. We're cool with the abbreviations. Sean, wake up. Listen, we're almost done. A physical property is a property you observe without changing something. Things like color, stuff like that. Emission spectrum are physical properties. They are physical properties. Another physical property is the state of matter something has. Solid, liquid, gas, plasma. This unit is titled atoms and energy, and solids have the lowest energy, and plasma has the highest energy. So it's solid, then liquid, then gas. And plasma is confusing because we use the same word for two different things in science. Plasma here is in fluorescent lights, it's in lightning, it's in the sun and other stars. It is a high-charged, fluidy, ionized gas. It is a gas, but it's a weird, fluid kind of gas that has super high energy. Lightning bolts. Just think of that, okay? The other use of plasma is in medicine. Anybody know what I'm talking about? Any of y'all in the health class and you know about plasma in biology? What is it? It's in your blood. Your blood appears to be red. But if I took your blood, and I used to work at a hospital lab, and I would do this, I put it in a test tube, and I centrifuged it, spun it around and around and around. The red cells would go to the bottom. The liquid of your blood is actually yellow. They say it's straw colored. And that's the plasma. What makes your blood red are the red cells, not the liquid itself. Yes?
Like cellular plasma?
Yes, you can. And yeah, you can. And there are places at West Georgia where they're always trying to get the college students to go sell their plasma and stuff.
I heard you get a lot of money.
You get like $50 every time. Yeah. So like you can do it 4 times pretty quick and have $200. So they advertise it at West Georgia College.
That involves needles, though.
It does. All right. So that's it for the notes. We have got a little over 30 minutes, and we're going to do some things. So science is great.